Lab 1. An object moving at the same speed in the same direction. The purpose of this lab is to explore constant velocity. This includes examining physics principles, observing and recording an object moving at constant velocity, developing a model using the mentioned physics principles, and comparing the model to the experimental data to check for accuracy, which this experiment happens to be very accurate. First, physics principles will be explored. Newton's second law, final velocity equals initial velocity plus the net force over the mass of the object times the change in time, can be used to calculate change in velocity. Since the velocity is assumed constant, F net is equal to the zero vector, setting the final velocity equal to the initial velocity. The next relevant equation is final position equals initial position plus the average velocity times the change in time. We can use the final velocity calculated in Newton's second law as the average velocity, since it's the same as the initial velocity. Since this equation gives the final position, running the calculation at small time intervals will give a graph of the position versus time data. Now, where did the initial values come from? This is where the experimental data is collected. I rolled a small bouncy ball across an air conditioning unit. I collected position and time data using Tracker. I chose to have the ball moving in the positive x direction on the axes. That was the experimental part. Now we open Python to begin working on the model. There are 4 variable conditions: mass of the ball, initial position, initial velocity, and start time. The mass of the ball was 10.8 grams in this instance. The initial position and the start time can be found by looking at the first row in Tracker. The start time is 0.033 seconds, and the initial position is 0.016 meters in the x direction. The last value, initial velocity, can be given by looking at the first 2 rows in Tracker. It's the change in position over the change in time, which gives the value of 0.4117 in the positive x direction. As mentioned before, the net force is equal to the zero vector. As mentioned before, if the 2 physics principles were run through a loop at small intervals, it would provide a position versus time graph. This is the Python code for that model. It uses time intervals of 0.01 seconds to graph the position of the ball up to 0.701 seconds, the interval in the video which I felt best displayed constant velocity. And this is the graphical result once the module is run. Now the question is, does this model work, or do bouncy balls defy physics? When the model position, the dotted blue line, was graphed against the experimental position, the results showed that the model is fairly accurate. It sometimes overpredicts the position, but it does this as often as it underpredicts it. This slight variation may be attributed to selecting not exactly the center of the ball on Tracker. A vector has direction and magnitude. So what if the axes were flipped? The direction of the vector would change, but the magnitude remained the same. This would be true for the velocity vector and the position vector. If the net forces were constant, it doesn't really matter individual forces. However, if the model overpredicted, we could account that to friction or drag. But as it stands, we cannot isolate individual forces. This is Physics 1 after all. So, the model accurately represents the observed motion, because the lines didn't deviate from the others. And it may be concluded that the object did move at a constant velocity, according to physics principles of Newton's second law. This experiment assumed that the object was too small for drag force to be an issue, and moved along a surface with limited friction.